Okay, so now demagnetizing magnets, right? The main idea for demagnetizing magnets is, of course, to cause the magnetic domains to point in random directions. Okay, so when previously they are all facing a certain direction in a magnet, that gives it its magnetic properties. What you want to do is make them point in random directions, and then they will lose that magnetic property. Following? Okay, so how do we make it go from all aligned to misaligned, right? Make them point in random directions. Then it will no longer be a magnet, right? How do we do this? We have three main ways we can do this. The first way is heating. What does heating do? Remember, these magnets in the magnetic domains are like atomic magnets, right? So these little magnets, they are basically the atoms. They kind of have a magnetic, they are like little magnets. When you heat them, you make them vibrate vigorously, and when they vibrate vigorously, they knock into one another and stuff like that. They start to turn and face in random directions. Okay, so basically when they start to turn and face in random directions, they will lose their alignment. Okay, what you need to do here is you need to let the magnets cool in the east-west directions to ensure that the domains do not realign. What does this mean? So typically you have a north-south direction, right? So this is a north, south, west compass, right? Remember we discussed that one of the properties of magnets is that they will naturally align to face the Earth's, align with the Earth's magnetic field, right? If you leave them alone. So similarly, even though you heat them and they start to face in random directions, they would have a tendency to realign themselves. All the little magnets will have a tendency to kind of realign themselves with the Earth's magnetic field, right? Just like how a big magnet would behave. So if you let it cool down, you heat it up, they are facing random directions, but you let them cool down in north-south direction, they might have a chance of still having quite a bit of magnetic properties, because all the magnetic domains might find themselves realigning to the Earth's magnetic field. So this won't be very effective in causing it to it won't be very effective in causing it to demagnetize. Okay, so what you want to do is to let it cool down in the east-west direction. Can you see this is the east-west direction? So that even if the magnetic dipoles kind of start to realign a bit and start to face north-south a bit, and even if they do, they won't be properly aligned to in one direction, and the direction will not be north south or south north, whichever way, right? So it basically won't realign back to a magnet. Okay, does that make sense? Okay. So that's the general principle. This idea of east-west direction is going to be used in it's a key idea in all the methods. Okay, so moving on. Second method is hammering. In hammering, you hammer a magnet in the east-west direction once again, and this alters the alignment of the magnetic domains and causes the magnet to lose its magnetism. Okay, I think you've learned this in primary school as well. They tell you don't drop the magnets. Why? Because when you drop the magnets, it will cause it to lose its magnetic effect. They probably didn't say much about this east-west direction thing, but it literally means you find the magnetic east-west. So maybe the magnetic north is here. You take the magnet and you face it east-west. You take a hammer and you hammer it. Okay, what does hammering it in this direction do? It literally turns the magnetic domains to face this direction. And when it turns the magnetic domains to face like this direction, it doesn't all instantly face in this direction, but it will start to align a bit more in this direction. But basically, when it turns to the east-west direction, but some of them want to face the north-south, so basically it will make all of it point in random directions. Okay, so you're hammering it in this direction, in the east-west direction. You will cause some of them want to face north, some of them will get affected by this. So just tilted, they'll be tilted all over and you'll be facing in random directions again. Okay, so this is hammering. The last method for demagnetization is the electrical method. which it makes sense because if there's an electrical method to magnetize a magnet, there must be an electrical method to demagnetize the magnet. Okay, so the electrical method is using an alternating current. What is an alternating current? An alternating current simply means it's a current that changes its direction constantly, alternates its direction constantly. So it's like it usually changes a couple of times, like 10, 20, 30, 40, 50, 60 times a second. So it would, from here, so direction will be here, and then it will change to here, and then direction will change to here, direction will change to here. Right. So recall we learned in direct current circuits, DC circuits, that a battery usually has a positive and negative, and the direction of current is always positive to negative. Right. What an alternating current is imagine this battery keeps flipping. Okay, it just keeps flipping and flipping and flipping and flipping and flipping. So the direction of the current will just keep changing and changing and changing and changing. That's an alternating current. Okay. So yeah. So what does the alternating current have to do with demagnetization? So if you remember in the previous video, we said that a solenoid, the direction of current flowing in a solenoid determines the magnetic effect of the solenoid. Right. So let's see in the first example, if let's say current is flowing in this direction. Okay, if current is flowing in this direction, then current flows up through the wire, behind and then back up again, behind and then back up again, behind and then back up again. So you get your current all flowing in this direction. Use your right hand grip rule. Can you use your right hand grip rule and tell me which direction is the current? In this case, it's not which direction is the current, which direction is the magnetic effect. Where's the magnetic north? Because of the solenoid. If you did it right, your right hand grip rule, you curl your fingers around the solenoid. So this is the solenoid. I'm curling my fingers around this way. My fingers are pointing up, and then my thumb is pointing here. So the effect is that my north pole is here. But what happens when the direction of the current flips? When the direction of the current flips, which happens just the next instant, it goes behind, it comes down, goes behind, it comes down, comes down, comes down, comes down. Now my fingers are curling around this way in front of the solenoid, and my thumb is pointing this way. So now my magnetic effect is this way. Right? Can you see that every time the current changes direction, the magnetic north, because of the solenoid, also changes direction? Right? So what I get with this AC current is a magnetic pole that just keeps flipping left, right, left, right, left, right, left, right. What do you think this effect has on dipoles? On the magnetic domains? So I keep using the term dipoles because it's actually the university term for the tiny magnets. Okay, so if you keep hearing me say that, that's the reason. So anyway, so all the domains, if they were facing in one direction, let me draw them in a different color. If all the domains, say, were facing this direction, because north is here, right, in this magnet, so currently they're all facing this direction. But when I have the current keep flipping, what will it cause the direction of these magnetic domains to do? It will start, let's say when the magnetic field is, say, this side, when the magnetic effect points this side, north, then they will start to try to turn to face this side, right? Because this is like, it's like putting a really, really strong magnet with this direction. So all of these magnetic domains will start to turn to face this direction. But in the next instant, the magnetic effect will flip to this side, and then they'll start turning to face this direction. And so you can imagine this constant flipping, flopping, flip-flopping will cause the magnetic domains to start to just point in random directions, right? Because it keeps like turning here and then turning here and then turning here and then turning here, right? But that's not all you need to do. You also need to from there withdraw the magnet slowly with the AC current on. Okay, you either do this, you either withdraw the magnet with the AC current on, or you can gradually reduce the AC current. Okay, meaning you just turn down the power of the turn down the electricity of of the circuit. Okay, so you either do this or do this. Why? Basically, as you reduce if you pull, let's talk about withdraw the magnet first. Okay, so if you withdraw the magnet, basically you're pulling it further and further away from the coil, and the effect that has is as you pull it further away from the coil, what it does is that the magnetic effect gets weaker and weaker and weaker, right? Because the magnetic, if the magnet is here, the magnetic effect of the coil doesn't, it gets weaker as it's further away from the coil, right? So what it does is that because it gets weaker and weaker, the effect of it flip-flopping will also get weaker and weaker and weaker, and so you start to get more and more random, okay? Because some will turn more, some will turn less, so or you just start turning a bit less pronounced than it did previously. So this will ensure that they will be pointing in really random directions. Okay, so if instead of withdrawing the magnet, if you cannot, if you have like a way to gradually reduce the AC current, this would also have the same effect as withdrawing the magnet slowly, because it also slowly reduces the effect of the magnetic effect of the solenoid. Okay, so basically this is by right the best way to do it, withdraw the magnet with the AC current on, but if you have a way to gradually reduce the AC current, this has the same effect as taking the magnet out of the solenoid and moving it further and further away. Okay, again, this should be done in which direction? It should be done in the east-west direction. Okay, so I hope this is clear. Yeah, so with that, you can go to your handout and try question 5. Okay, so if you look at it, it says learning objective 3, right? You're expected to describe electrical methods of magnetization and demagnetization. Okay, so we're looking at learning objective 3, question 5. Do this question. After you've done it, you can resume the video and see if you did it right. So the diagram shows how a steel bar can be magnetized. Which statement describes how the steel bar can be demagnetized? Okay, so how can it be demagnetized? The answer should be use an AC supply. You want it to be flipping back and forth, and gradually decrease the current in the circuit. Okay, so answer is C. Not gradually increase, but gradually decrease, because it has the same effect as slowly taking it out and moving it further and further away. Okay, so the answer is C. Okay, fairly simple. And with that, we've come to the end of this portion of this topic, magnetization and demagnetization. How can we magnetize magnetic materials? Summary, there are two main methods. One is stroking, the other is using a direct current, putting it at a steel bar in a solenoid. Okay, and the main principle is aligning all the magnetic domains. Okay, how can we demagnetize materials? Demagnetize magnets. Basically, we want to unalign the magnetic domains, and we can do that by heating, hammering, and putting in an AC circuit and withdrawing it slowly. Okay, I hope that was clear. Okay, we've done question 4 already. Okay, great. I'll catch you in the next lesson.